Hi everyone, welcome to the second day of section 5.3. Today we are going to talk about what I'll call the shortcut method of evaluating definite integrals. Essentially, it's analogous to all the shortcut methods that you learn to evaluate derivatives. So for example, when we started with derivatives, we used the limit definition of derivatives, but we eventually transitioned into the rules for derivatives, like the derivative of x squared is 2x, and the derivative of the sine is the cosine, and the derivative of the natural log of x is 1 over x, and so on. And we're going to do the same thing today with the integral. So I wanted to remind you that the integral of the sine function from 0 to pi is equal to 2, and that's why we're looking at the 5.2 day 2 notes. And today we are going to learn what is called the fundamental theorem of calculus. And it has two parts, and we are learning about the evaluation part. And to do that, we're going to start out with any function. Now, I am going to start out with the sine function because that one we are familiar with its integral from 0 to pi. We know that that value is 2. And to help us with this, I am going to use a Desmos demonstration. And what you see here on this Desmos demonstration is a graph of what is called a definite integral. It's an integral that has specific lower bound and upper bound. And this integral is represented by the shaded region in red here between the function sine of t and the x-axis. And as you can see, that value is 2. So if you look at the third line in the upper right, it says that the integral from a to b of f of t dt is equal to 2. A is 0 and b is pi. So that's not what we're really all that interested in today. What we're interested in is the rest of this. So the next thing I'm going to do is I'm going to graph. If you look at line 6, I've defined a new function using the capital letter f. And that function, capital F of x, is defined as the integral from a to x of f of t dt, which in this case is the integral from 0 to whatever x value we pick of the sine function. So let me highlight that, and you will see the curve in blue. And that's, again, not what we're all that interested in. What we're going to do is we're going to build up to what we're interested in. The next thing I'm going to do is I'm going to plot a point on that function, and that point is going to correspond to the upper bound of our integral, which currently is pi, and the value of capital F of x at that upper bound. So let me turn that on, and you will see that green point just appeared there, and it is directly above the red point because they have the same x coordinate, which is equal to pi. And I'm going to label that. And the y coordinate, as you can see, of that green point is 2, which is the value of the integral of the sine function from 0 to pi. So in other words, if I were to change the y value, the upper bound, and let's just for confirmation's sake change that to half of pi, or 1.571 approximately, you will see that the integral from 0 to pi over 2 of the sine function is 1. Again, that's not what we're specifically interested in. So let me change this back to 3.14159 and move on. What we're really interested in is what comes next. So in a minute here, I'm going to graph the derivative of capital F of x. And to see that, I'm going to click this button and watch what happens to the graph of the sine function. Watch what happens to the red graph. You'll notice it turned green. So what does that mean? That means that the derivative of the integral of the sine function is the sine function. What does that mean? That means that the integral is the antiderivative of the derivative. Another way you might think of this is in terms of inverses of each other. Essentially, the derivative and the integral undo each other. And to illustrate that further, I am going to pick some other functions to illustrate that. So instead of the sine function, let's say we pick the function f of t is equal to 2. And so we have the constant 2, and I'm going to pick an easier upper bound of integration. We'll just make that 3. So you will see that if we integrate the function f of t is equal to 2 from 0 to 3, the shaded area in red there represents the integral, and the point on capital F of x at x equal 3 has coordinates 3, 6, and 6 is the value of the integral. I'm going to turn off the f of t equal 2 for a moment, and I am going to turn on the derivative. Oh, it's not going to let me turn on the derivative. It's a constant, but you can see that it's equal to 2. So again, the derivative of the integral is equal to the original function. To illustrate that further, let's pick another function. So we'll use f of t is equal to t. And f of t is equal to t is the red line shown there. And we're going to integrate that from 0 to 3. And as you know, the area of a triangle is 1/2 base times height. So 1/2 times 3 times 3 is 4.5. And the blue function, again, is representing the value of the integral at any upper bound if we're starting at 0. But what I want you to notice here is I want you to notice when I turn off the derivative of capital F of x, we have the original function, f of t is equal to t. When I turn it back on, that turns green. So again, confirming the idea that the derivative of the integral is the original function, or that the integral is the antiderivative of the derivative. So let's go back to our notes and put down what we have. So second, number 2, what did we just show? We defined capital F of x to be the integral from a to x of f of t dt. And we just showed that the derivative of big or capital F of x, which is the derivative of the integral from a to x of f of t dt, is equal to f of x. In other words, the derivative and the integral are essentially inverses of each other. And this part right here that I'm putting a box around right now is the fundamental theorem of calculus, which we use for the evaluation part today. So I want to do some examples. And on the left, I'm going to write down the function. And on the right, I'm going to write down its antiderivative. So function and antiderivative. And you can verify this by integrating the antiderivative to see that you get the function. So we'll start out with something simple like f of x is equal to x squared. And you're thinking, okay, what would I have to integrate to get x squared? Well, you'd have to integrate an x cubed function, but you would need a constant of 1/3 out in front. So when you use the power rule, the 3 of the exponent and the 1/3 coefficient cancel each other out. But you could also say the following. You could say that we can put any constant we want on there because the derivative of that constant is going to be 0. So in other words, if we integrate big f of x, or if we take the derivative of big f of x, we get little f of x. Another example, f of x is equal to the cosine of x. So big f of x, or capital F of x, is going to be equal to the sine of x plus any constant. The antiderivative of 1 over x is the natural log of x, again, plus any constant. And we'll throw a polynomial in here. The antiderivative of 3x squared plus 10x plus 1 is going to be, well, let's see, what are we going to have? We're going to have an x cubed plus a 5x squared plus x plus a constant. And again, to verify that you did this correctly, take the derivative of capital F of x and verify that you get little f of x. So how does this help us evaluate integrals? Well, this next part gets a little bit heavy in terms of proof, but we're going to do it anyway. And it goes like this. If the derivative of the integral from a to x of f of t dt is equal to f of x, which is basically the fundamental theorem of calculus, then the antiderivative of the derivative of the integral from a to x of f of t dt is equal to the antiderivative of little f of x. Essentially, we're taking the antiderivative of both sides. So we happen to know that that is equal to big f of x. Okay? So, since we know that big f of x is equal to the antiderivative of little f of x, then we can say the following. The integral from a to x of f of t dt is equal to f of x plus any constant. And that's because if we take the derivative of both the left and the right side, we're going to get f of x. Therefore, remember these three dots represent therefore, the integral from a to a of f of t dt is going to be equal to big f of a plus some constant. But we know that the left-hand side from properties of integrals is 0, and that tells us that the constant is equal to the opposite of f of a. Now you might be thinking, okay, well, what's the point of all this? Here's the point of all this. The point of all this is the following. The integral from a to x of f of t dt is equal to f of x plus c, which is equal to f of x minus f of a. Why is that important? Because we just showed if we want to integrate a function from any lower bound a to any upper bound x, we can take its antiderivative at x and evaluate that, take its antiderivative at a and evaluate that, and take the difference of those two values, and we have the integral. So I'd like to do a few examples here. Let's start out with the integral from 0 to pi. That's a very sloppy integral symbol, but it'll do, of sine of t dt. We already know what that value is. We know it's equal to 2. But the antiderivative of the sine function, Well, what function, when I take its derivative, will give me the sine? The derivative of the cosine is the opposite of the sine, so the antiderivative is the opposite of the cosine of t. A little bit about notation here. Sometimes we put the following. We want to evaluate that antiderivative at the lower bound 0 and the upper bound pi, so I'm going to do it that way. So let's take the opposite of the cosine of pi, that's my upper bound, and subtract from that the opposite of the cosine of 0. So let's see. We get the opposite of the cosine of pi is -1 minus the opposite of the cosine of 0, which is going to be 1, and we get the following. We get 1 plus 1, which is equal to 2, which we know to be the case. Let's try that again, except let's go from pi over 2 to pi of the sine of t dt. Again, the antiderivative of the sine is the opposite of the cosine of t, and we're going to evaluate that at a lower bound of pi over 2 and an upper bound of pi. So we have the opposite of the cosine of pi minus the opposite of the cosine of pi over 2, and that is going to be the opposite of -1 plus 0, or +1. So evaluating integrals becomes much easier now that we know this shortcut technique. And one last example from a geometric point of view. The integral from 5 to 10 of 3 du. Remember, that u is just a dummy variable. So what is the antiderivative of the constant 3? It is 3x, because when we differentiate that, we would get 3 from 5 to 10. So we would have 3 times 10 minus 3 times 5, which would be equal to 30 minus 15, which is equal to 15. And if you want to verify that geometrically, the constant 3 is just a horizontal line, and we're going to go from 5 to 10. So we are basically finding this shaded area right here, and you can tell that we have a height of 3 for our rectangle and a length of 5. So this area right here is 15. So, in summary, the integral from a to x of f of t dt can be found by finding the antiderivative and evaluating it at the upper bound minus the antiderivative evaluated at the lower bound. And that is the fundamental theorem of calculus, the evaluation part. The second part we will talk about later.